Lee Aucott, Head of Materials Science and Technology at UK Fusion Energy Limited. Lee.
So, good morning everyone. It's a pleasure to be here speaking to you all today alongside my esteemed colleagues from the fusion sector in this fusion focused session. So today I'm going to be talking to you about the STEP Fusion program and how we are building industrial capability for a global fusion market. STEP is an acronym for Spherical Tokamak for Energy Production, and the STEP mission is to deliver a UK prototype energy plant targeting 2040 and a path to commercial viability of fusion. But it's much more than just a fusion power plant demonstration. Through the delivery of the STEP prototype plant, we will build a fusion supply chain, and through that create significant social value through the jobs that we create and the skilled workers that we need to fill those jobs. Also the investment that we are going to be placing nationally, but really actually focused in the region where we're building the prototype plant is going to be hugely valuable for the region. And this is going to drive significant UK economic value through the contracts that we're placing with this emerging industry, but also through the likely organisations that we will need to spin off as a result of the novel technology development that we are undertaking. And ultimately, at the end of all of this, we will have a sovereign UK fusion technology landscape that we can then export out to the wider world and bring in international investment to UK PLC. Nobody has ever done this before. So the information baseline that we're creating in terms of activities, costs, schedules, successes, lessons learned, etc., is incredibly valuable information which will really help us streamline delivery of future commercial plants which will follow the prototype. Once we complete all of this, we demonstrate our major technical and programmatic objectives. We will have a global fusion facility, which we can then use well into the future for things such as advanced materials testing and qualification, the development of advanced components and systems, and the qualification of those in a real fusion environment. And that's really, really important, as that environment doesn't currently exist and is a major challenge for us in delivering the prototype. So it's much more than just a prototype plant. The way we're delivering this program is through an integrated delivery team that we call the STEP Fusion program. And STEP Fusion is led by UK Fusion Energy. UK Fusion Energy's role is to deliver the STEP Fusion program, but also successive fusion power plants acting as the national fusion systems integrator and working with partners and industry to develop and deploy the capabilities and technologies which are required to deliver fusion power to the world. We've been working with our fusion partner for well over a year now, UK Atomic Energy Authority National Fusion Research Laboratory, and more recently we onboarded our construction partner, the ILIOS Consortium, which is led by Nuvia and Kier Group. We paused the selection of our engineering partner and instead moved ahead with the onboarding of strategic suppliers, and most notable of that probably the recent announcement of Tokamak Energy as our magnet system partner. And there's actually a multitude of opportunities in this space that are currently live. So at the end of the presentation I have a link to our procurement portal, and we have supplier events next week, and I just really want to highlight that there are significant opportunities in things such as breeder blankets, systems engineering, control systems, and many more at this level, and also much further afield within the supply chain. Why we're doing all of this is really building for the future. If we look at the electricity generation mix in 2024, it is still predominantly dominated by fossil fuels. So around 60% of the world's electricity generated from fossil fuel. If we look at the global demand profile, we can see a clear shift towards green energies. And if we look at the global growth rates down here, we can see that the demand in 2024 increased 2.2%. That's about double the annual increase that occurred over the prior decade. So effectively what we have is an exponential, the beginning of an exponential growth in demand coupled with a huge shift towards green energy. And we really believe that fusion energy has a critical role to play in this future energy mix, providing safe, clean and reliable baseload energy to the grid in what we believe will be a multi-trillion pound industry and really feeding the growing demands that we have for electricity in the electrification of our transport systems, but also the emergence and explosion of AI into the world. So it's a huge opportunity and one that we really need to harness. The path we have to deliver this program is illustrated in the high-level schedule here. We began in 2020 and began the conceptual design phase, 4-step. So in this phase, we developed a conceptual design, selected a site and designed the organisational delivery model, which I just talked about. And we're now into what we call tranche 2B, where we are maturing the engineering design, really scaling our technology demonstration program to underwrite our confidence in the design and really cracking on now with the site enabling works and characterizations. In terms of manufacturing, the bulk of the manufacturing of real components and systems 4-step is planned to take place through the 2030s, with the aim to assemble and then operate in the 2040s. However, in order to get to full-scale manufacture, we need to do an incredible amount of manufacturing development to develop the fairly novel and exotic technologies that we need and scale them to a point at which a supply chain is able to actually deliver the components and systems that we need. So while 2030s manufacturing might seem a few years away, the manufacturing development work that we need to undertake is here now, and there's a lot to do. So huge opportunities for people to get involved in this program. In the next few slides, I'll talk a little bit about the design progression, the site progression, and finally the technology demonstration program linked to manufacturing development. So in terms of the design, STEP is a spherical tokamak. So a spherical tokamak basically is a form of magnetic confinement fusion. We use superconducting magnets to confine and control our superheated plasma, which is a mixture of deuterium and tritium fuel, and confine that away from the metallic walls of our sort of structural system. So it's quite different to, this morning was very sort of fission focused. We have a slightly different challenge. This is not a proven technology. We've got a lot of work to do in the R&D space to sort of develop this in the near term before we deploy it. And we're basically incrementally maturing the design that we have. The latest sort of public release is our SPP 02.4 baseline, which we released in September 2025. And in December 25, we sort of formally moved away from concept design and into preliminary design. And the image you can see on the far right here is basically like a London Tube map of the STEP plant. And this was produced by the team to highlight the highly interconnected, complex nature of this system of systems that we are designing ahead and then manufacturing and delivering. And what I really wanted to sort of highlight on this particular point here is that much of our focus at the minute is in zone 1 on the tokamak. The tokamak is the really unique, first of a kind, difficult piece of the plant. That is where we are focusing a lot of our efforts. But if you look at zone 2 outwards, it is going to be very similar to any conventional power plant, fission, coal, gas, or other that you see. So in terms of industry getting involved, there is huge opportunity to get involved in the highly exotic tokamak center, but also for conventional industry which are supplying into power plants at the minute, that opportunity will be the same here. All of this is happening at West Burton. West Burton is the home for STEP, and a digital representation of the site is in the top left. We opened our first offices on the site in January 2024 and really started straight away on the site characterization works. In November 2025, we selected the site, the location for the tokamak, which will be on the south of site. And as you can see from the image, the sort of tokamak facility and plant only takes up a proportion of the site that we own. So there's ample opportunity for businesses to come and co-locate on this site in the future. Site selection really enabled us to begin the development consent order process, which began in January, and most recently we've tripled the size of our office space on site to cater for the rapidly growing team that we have based in West Burton. And this is obviously a hugely collaborative programme with the local councils and local people. Final slide from me is related to the technology demonstration programme and really focusing on manufacturing development in particular. And what we really need to do across the whole of the tokamak really is translate very quickly and efficiently from manufacturing discovery into industrial delivery. And the images which you can see on the slide are related to our inboard shielding system. So the inboard shield is basically a hollow column of tungsten and tungsten ceramic blocks, which are assembled almost like a brick wall around our central column magnets. And they're there to protect those center column magnets from the neutron bombardment from the plasma. The neutrons degrade the high temperature superconducting magnets and then reduce the life of the machine and overall plant. So we need to protect them with neutron shielding materials. One of the particular challenges we have is how do we bond these refractory metal / ceramic blocks to steel coolant tubes. So we've been working with academia to discover a joining process which is both metallurgically sound but also, more importantly, scalable to the vast size and weight that this overall system will be upon delivery. So we've been discovering the process and patented a range of patents in around this technology, and then began to scale towards our sort of final component scale through high value manufacturing catapult network. More work needs to be done on the scaling and translation, and then eventually we really need to put this out to industry to deliver. There is no industry that exists to do this, so what do we do there? We've got options to maybe use an adjacent industry and try and convince them to sort of tailor a bit of their business to do this, or maybe more likely spin out a new organisation using the patents and IP that we've developed to deliver this system in the future. So this is just one example of one manufacturing challenge related to one particular component or system. Our challenges are vast, they're diverse, and we really need to be collaborating and working with a whole spectrum of sort of academic, SME, innovative type companies right through the catapult network and RTOs for scaling technologies, and then out to existing and new industry in order to deliver our manufacturing development program. So yeah, again, huge opportunities of organisations of all sizes to get involved in this program, and I think we've got a breakout session actually just after lunch where I think we'll be able to talk a bit more about the broader manufacturing challenges. So on that note, I'm going to close. There is a link to our procurement portal on the slides. I don't know whether slides get shared with audience, but I'm sure if you Google UK Fusion Energy procurement portal, you will see our current and future opportunities that are coming out. So thank you very much.
Sorry, I'm going to